Hello everyone and welcome to This Explainer. Today we're diving into a really fantastic theoretical study by Miguel Arteaga Varela. It's titled First Principles Investigation of the Mechanical Properties of CdAg and CdAu Bimetallic Nanowires. This research was presented at the 34th International Materials Research Congress, that's IMRC 2026, and it gives us a highly targeted professional look at bimetallic systems and what these complex nanoscale structures can actually do. Here's our roadmap for the briefing. We'll start with a quick introduction, look at the computational methodology, dive into the structural and mechanical properties, do a comparison of CfDlG and CfDAu, and then wrap up with some conclusions. Let's jump straight into Section 1, Introduction to Metallic Nanowire Applications. Now, as you probably know, these structures are getting a ton of attention across the scientific community right now, and for good reason. Their unique electrical, thermal, and mechanical properties make them incredibly promising candidates for next-generation nanoelectronics, nanomechanics, and thermal management. This specific study zeroes in on bimetallic CdAg and CdAu nanowires, evaluating their mechanical properties and, really excitingly, their potential for shape memory behavior. All right, moving to Section 2, Computational Methodology and Modeling Parameters. To get reliable theoretical results, the modeling parameters had to be incredibly precise. Step 1. The calculations relied on density functional theory, or DFT, implemented in the Siesta code using a 2x2 unit cell. Step 2. They optimized the parameters using the Generalized Gradient Approximation, or GGA. And Step 3. They locked in an optimal mesh cutoff of exactly 120 Ri. That level of precision also dictates the growth directions, meaning the structural optimization required very specific K-point sampling grids. If we look at the 111 growth direction, a 7x1x1 grid was used. On the flip side, for the 110 direction, it was a 1x7x1 grid. This rigorous optimization phase was absolutely crucial. It allowed the researchers to pin down the equilibrium configurations and really understand how the geometry of these specific nanowires drives their overall physical effects. Which brings us to Section 3, Structural and Mechanical Properties, where we analyze the mechanical response. A major parameter analyzed in this work was Poisson's ratio, and the calculated values ranged from -0.1 to -1.0. Now, if you work with materials, you know that negative values like that are highly characteristic of a very specific and highly sought-after class of materials. We're talking about auxetic behavior. It's that incredible property where a structure actually expands laterally when you stretch it. It's completely the opposite of conventional materials that just thin out when pulled. This auxetic behavior is exactly why these bimetallic nanowires are such a game changer for advanced mechanical applications. Let's break down Section 4, comparing CdAg and CdAu, specifically focusing on their anisotropic responses. When we put these two side by side, the CdAg system yields a value of 14.92 along the XC direction. This means it's incredibly well suited for lightweight structures and devices operating under variable loads. The CU system, however, comes in with a value of 12.05. That highlights its potential for some really different real-world uses. Think flexible electronics and advanced coding applications. Finally, Section 5, Conclusions and our summary of mechanical behavior. Ultimately, thanks to rigorous geometric optimizations and the discovery of those negative Poisson's ratios, it is clear that CADS-based bimetallic nanowires demonstrate immense potential as candidates for mechanical metamaterials and nanoscale functional devices. Thank you for your attention.